Okay, very welcome to all of you today. And today we will be talking about the very basic equation of quantum mechanics, what's called as Schrodinger's wave equation. And before we actually will talk about this equation, we would like to write down this equation and we would like to be familiar with the symbols that are associated with this equation. And before we talk about this equation, I would like to go back to the time of 1920s. It was the time of chaos in the world of physics, because physics was thought to be complete. The Newtonian mechanics was assumed to be a complete mathematical modeling of the universe. And people thought that we can explain everything, whatever happens in this cosmos, whatever happens in this universe. And this whole universe was taken as a closed machine, and actions taking place in that machine, and presumably it was thought that we could predict every action of the universe. But in the same era, at the same time, there was a chaos. The chaos came in action when people looked at microscopic systems, when people looked at light, what we call as photons. The light was assumed to be an electromagnetic wave, and they could see the dual nature of light. The light could behave like a wave under certain circumstances, as we call as photoelectric effect, and it could behave like a particle in case of photoelectric effect. And to explain the double slit experiment, you had to assume that light is an electromagnetic wave. And you could not probably predict the motion of electron around the nucleus. So there was a chaos. And in this time, we had two developments. And one development was from de Broglie, because de Broglie came up with an equation known as de Broglie equation that tells us that material particles have dual nature. Because if light has dual nature, then from de Broglie point of view, material particles must also have dual nature. And it was the time Schrodinger was working on the problem. And he was asked to deliver a lecture on de Broglie equation. And he gave two lectures on de Broglie equation. And Debye, it was basically proposed by Debye. Debye had asked Schrodinger to deliver a lecture on de Broglie equation. And when he delivered a lecture on de Broglie equation, the question was raised by Debye. And the question was, come on, you are saying that you have material particles and these material particles have waves associated with it, then these waves must be represented by some mathematical equation. Because for other waves you have equations, for sound wave you have an equation, right? For electromagnetic waves you have an equation. It was basically the question raised by Debye in that presentation that was given by Erwin Schrodinger in those times. And Schrodinger worked, and he worked hard, and he came up with the very famous equation known as Schrodinger's wave equation. And Schrodinger's wave equation, it encompasses the energy of the particles, it encompasses the wave nature of the particles. So he was successful in in discovering, in developing a model for the material waves. And that model is given by Schrodinger's wave equation. And as we understand that we have generally talked about the vectors, we talked about the vector space, we talked about the Hilbert space, we talked about a range of mathematical formulations that are essential in how to work out the problems of vectors. So what we have a very fundamental vector in Schrodinger's formalism, and that is called as a wave function. And you may call it as an eigenvector when you work in the framework of bracket notations. So the point is that this wave function, this state vector, the same thing. If we choose it as psi, and this psi is the function of the position and time, right? And this psi is basically the solution of Schrodinger's wave equation. And we would like to frame our Schrodinger's equation starting from this psi, right? And this psi is written in the form of an exponential function with an amplitude a, e to the power of I kx minus omega t. Now looking at this equation, you can see that this psi is comprising both the momentum, because k is linked with the momentum of the particle, and it is also comprising the energy, omega. Omega is the angular frequency, right? And all of you know we have the Planck's equation, E is equal to h cross omega, right? So you can see this wave function as a composition of both the momentum of the particle and the energy of the particle, right? So this is how this vector is written, this wave function is written. And this wave function is carrying the solution of the Schrodinger's wave equation. Now, in order to proceed from here, before I proceed, because the equation is demanding the differentiation, obviously you have the different functions involved in this exponential. So obviously you'll be using the partial derivatives while differentiating out this equation. So if I take an ideal system and I assume that the total energy of this ideal system is E, right? This is total energy. This total energy must be the algebraic sum of kinetic energy and potential energy, right? So for kinetic energy, I can use this E is, for kinetic energy, it's 1 half of mv squared. I can write down this as p squared by 2m, right? Plus, since I'm choosing my wave function along x, so the potential I will use here as the function of x, right? So your total energy is the sum of kinetic energy and the potential energy. So from here, I can calculate this p squared. I can do that. So what will be that p squared? Yeah, p squared will be 2m times E minus V of x, right? And for P, you will have under root of 2m E minus V of x, right? Now, if I go back to my equation, if I go back to this wave function, and what's that wave function? That is psi as the function of position and time. Now, what does this psi carry? It carries the complete information about your system. It carries it completely. And we can see this psi is a complex function, because in the exponential of that function is what? You have an iota. So ae to the power of I kx minus omega t. So again, I would like to tell you, this k is you may call it a propagation vector. So it's giving you the wave nature of your material particle, right? And at the same time, you can convert it in terms of the momentum. So this wave has momentum, right? And this omega is giving us the energy that's associated with our particle, right? Now, if I differentiate this equation, first I would like to differentiate this equation with respect to time. Now, if I do that, if I differentiate it with respect to the time, come on. Yeah. So what I'll get? I'll get dou psi by dou t. The psi is a function of x and t. We know that, and this must be equal to. You will have minus I omega a e to the power of I kx minus omega t. This is it, right? Okay, that's fine. So now you can see, I can write down another step. This is dou psi by dou t. Okay, now we understand this psi is the function of x and t. I wouldn't write that again. Okay, so this will be equal to minus I omega. For this I can use psi, right? That we can do. Now, you see, omega is what? It's an angular frequency. Now, what shape it is taking basically? See, this omega is acting on the wave function. It's acting on psi. What do you consider this omega? It's acting on psi. It's an operator. It's an operator. So I can think of this omega as, if I talk about E, Planck's equation, we have E is equal to h nu, isn't it? Now, we can think of E is h by 2 pi times 2 pi nu. I can do this. So this is my h bar, and this is my omega. So E is h bar omega. So this omega is going to be E by h bar. Are you getting it? So here, instead of omega, I would like to write down E. But this E is my operator. This is my energy operator. It's acting on the state. It's acting on this eigenfunction psi. Are you getting it? Okay. Can we proceed? Okay. So now, what we have? We have minus, instead of omega, I will write E by h bar, and then you have psi here, and this will be equal to dou by dou t of psi, isn't it? So this E psi will give you what? This h cross will go up, this iota will come down, so this is minus iota, and you will be left with dou by dou t and psi, right? And you can multiply by iota, so this will become iota. Here you will have iota square. Iota square will give you minus 1. That minus 1 will cancel with this minus, so you will be left with E psi equals an operator. Now see, the right hand side is telling me that in the left hand side, behind the wave function, you have an operator. Okay? So what is that operator? Now this is an indicator of the fact that this is an operator. So it's E cap. This is energy operator, right? So I can write down this energy operator. So what is this energy operator? Energy operator is I h bar dou by dou t. You can see it's all about, I have just replaced the wave function from both sides. When I replace it, what I obtain the energy operator, isn't it? Okay. Now, again, I'll go back to that equation, right? And I would like to differentiate that equation with respect to the position. So, differentiating the wave function psi with respect to x will give me what? It will give me dou psi by dou x is, yeah, what is it? It is iota k, and then a e to the power of I kx minus omega t. Right? Fine? Okay. So this must be equal to I k psi. Right? Now, in the left hand side, I have the partial derivative of psi with respect to the position. Now, in the right hand side, what I have k. What's k? K is a propagation vector. What k is equal to? K is equal to 2 pi by lambda, isn't it? Okay? And for lambda, what I have? This is 2 pi by lambda is h by p. So p will go up. So this 2 pi by h is 1 by h bar, right? So what you will have here? You will have k equals p by h bar. Is it true? So I can use this p for this k in this equation. So if I do that, what I'll come up with? Yeah, I'll come up with? Yeah?
Dou psi by dou x.
That will be on the right hand side. Tell me what?
P by h.
P by h bar, then dou psi by dou x is,
Dou psi.
no, you told me.
Only psi.
Yeah, it's only psi here. Okay, psi is,
Dou psi by dou x.
this is dou psi by dou x. This is it, okay? That's fine. So this h bar will go up, iota will come down. So you will have p psi is h bar by I, then dou psi by dou x. Right? Okay, in the left hand side you have the momentum operator now. Because in the right hand side you have a differential. It's an operator. And what's an operator? It's a mathematical machine. It's a mathematical machine that acts on your wave function and you obtain the result out of it. So this is p cap. So if I remove the wave function from both the sides, what I'll get this momentum operator is, I can multiply and divide by iota. So this will be minus I h bar dou by dou x. Okay? In quantum framework, where we deal with operators are basically replacing the observables that we have in classical mechanics. And in addition to that, we have these special operators. They are Hermitian operators, right? So this is your momentum operator. That was your energy operator. Then you can have kinetic energy operator. You can have position operator, right? So these kinds of things will automatically evolve as you move on. Okay, now let's go back. Let's go back to that equation. The equation that I took the derivative with respect to x, right? What was that equation? That was
Psi of x.
dou psi by dou x is iota k and psi. This was it. Now I should write down psi as a whole because this is e to the power of I kx minus omega t. Right? Yeah, a is with it. A is with it. You're right. Okay. Now I would like to differentiate this equation again. So if I differentiate it again, what I'll get? I'll get the double derivative of psi with respect to x. You will have another iota, that will give you iota square. Iota square will give you minus here. And you will have k square. And you will have a e to the power of I times kx minus omega t. Now, for this thing, I can again write down my wave function psi. So what I'll get out of here? I'll get the double derivative of psi with respect to x.
Minus k.
That is equal to minus k square. But I have a relation between k and p, right? So this will be minus p square by h cross square, right? And then you will have your original psi. Fine? Now, you remember I calculated this p square. I took an ideal system of which we have the total energy equal to E. And that is the algebraic sum of the kinetic energy and the potential energy. From that equation, I calculated the momentum square. So what was that? That was, so this is minus, that was 2m by h cross square is here. Then you will have E minus V of x psi. Right? Now you can see in this equation, you don't find any time, right? So this is, you are going to obtain a differential equation, Schrodinger's wave equation, and this equation is independent in time. So this equation can be used in the situations where there is no evolution of the time, right? The electron is in the orbit, and it may be in another orbit, right? So you will be using this equation in those situations where there is no evolution of time. So what will be your equation now? I can write down this equation. Yeah. You will have an equation. This is dou 2 psi by dou x2. I will transform everything from the right hand side. So this will be plus 2m by h cross square E minus V of x of psi is equal to 0. Right? So we started with the wave function, talking about that wave function. Write down it as the mixture of k's and omegas, and assuming only one direction. But you can have a situation in which you have all the three directions. If you have all the three directions, this dou square psi by dou x2 will be what? It will be dou 2 by dou x2 plus dou 2 by dou y2 plus dou 2 by dou z2. You can keep psi outside, and then you will have the same thing. Plus 2m by h cross square E minus V of psi is equal to 0. Now, what is this? This is a Laplacian, right? So we can write down the Laplacian for this, and we can write down this time-independent Schrodinger's wave equation in 3 dimensions. So what will be that? That will be del square psi plus 2m by h cross square E minus V of psi as a function of x, y, and z is equal to 0. Right? So this is our Schrodinger's time independent equation. Now, I want to go more fundamental because Schrodinger gave us an equation which comprises both the dependence of time and independence of time. Right? So how can we achieve that equation? Is this clear to you? Okay. Now see, again, take an ideal system. It will have a total energy equal to E, right? You think in terms of E, and you think in terms of kinetic energy, and you think in terms of potential energy, isn't it? Are you getting my point? Now, these are classical, if they are classical observables, I would like to replace them by operators, right? So if I do that, what I'll have E cap acting on psi. Psi is dependent on position and time, is equal to K. K is what? It is P cap square by 2m. With it I have psi, right? Plus, I will replace this V by its operator, V operator of x. Are you getting it? Come on. We are going to write down the very fundamental equation. An equation that is the backbone of the quantum mechanics. This is the equation for which Erwin Schrodinger worked. And he worked to achieve this equation by the question that was raised by his teacher in the classroom where he was delivering a lecture on the Bragg equation. And he asked his student, if you have material particles having waves with them, then these waves should be described by a differential equation. There must be an equation, a modeled equation that will describe the wave, the material particle wave. So for E, what I have the operator. We calculated that. What was that? That was I h bar dou by dou t of psi is equal to. Now you have the square of the operator. So that will be minus, because iota square will become minus, and then finally a minus will retain here. So you will get minus h bar square by 2m dou 2 by dou x2 and plus v of x. Right? So I have to keep a psi outside. Now inside these parentheses, inside this bracket, we have an operator. It's an operator of kinetic energy and an operator of the potential energy. The combination of these two operators is called Hamiltonian operator. Right? So I can replace this body by the Hamiltonian operator. See? Kinetic energy operator, it's a Hermitian operator. Then you have the potential energy operator, it's a Hermitian operator. Then you have the combination of the two will make up the Hamiltonian operator. So Hamiltonian operator is a Hermitian operator. So I can write down this beautiful equation that was developed by Erwin Schrodinger. I can write down this as I h bar dou by dou t of psi is equal to h psi. This is that beautiful equation that was developed by Erwin Schrodinger. And believe me, the moment this equation was developed, at the same time there was the matrix formalism developed by Heisenberg. And the two formalisms were representing the same problem. And it was concluded that Schrodinger's picture and Heisenberg's picture, they are the two faces of the same mathematical coin. With this, if anybody has any queries, you can ask me. So with this, I would like to end this talk, right? Yeah.
Why psi is a complex number? Why we can take as
Because you are claiming that it carries all information about the system, and your system is complex. See, if everything is simple, real, I would like to have psi as a real number. But when I look at the system, the microscopic system I'm talking about, the microscopic system is complex. It has infinite probabilities. It has infinite possibilities. You remember the imaginal Hilbert space that we talked about? I said that this mathematical space carries everything. Now, what do you mean by everything? It means everything that's complex, everything that's real, everything that's simple. So, when you write down Newton's second law, how do you write it? You write it as an ideal equation, that force is the rate of change of momentum, right? And there you have complete predictability, right? You are completely predicting your system. Now here you have the bone of Heisenberg's uncertainty principle. You have complexity. You can, even that's why it doesn't have a physical implication. Whenever we say psi, do we say it has physical applications? Why? Because you cannot convert it into the numbers. In physics, what we do? We convert things into the numbers. That's what physics is, right? So that's why psi doesn't have the physical implications. For that, we take the advantage of its dual Hilbert space. We take advantage of its complex conjugate. And then we calculate all of those probabilities. So where the wave is dancing much, the probability of particle being there is maximum. Where the wave is dancing less, the probability of finding that particle is less. So, not having the physical implications of this wave function is telling us that why this wave function has to be a complex function.
Okay, sir, thank you.
Okay, so you can.